Welcome to the third part of 2.3 continuity, where we'll discuss the three main types of discontinuities. Recall the definition for continuity said that our function had to be defined at, we called it C, in this case we'll say A. Our function has to be defined at A. The limit as x approaches A has to exist, and whatever the function is and whatever the limit is, those have to equal. Well, if we look at our jump discontinuity, we're literally jumping from one point to another. Think of like a little person up here. They'd have to jump to get down here or jump to get from here to here. We can clearly see here that the limit as x goes to A does not exist. The left limit and the right limit are not the same. So a jump discontinuity most often happens with piecewise functions, and we would say a jump discontinuity breaks the rule because the limit as x approaches our number, it could be A, C, whatever, our limit does not exist. All right, for a removable discontinuity, it has this word removable because the discontinuity is very easily removed. It's easy to make this type of graph continuous. If we take a look here, there's a hole. Our function is not defined at A, so that's one way that we could have a removable discontinuity. Our function at A is undefined. But it would be very easy to fill in the hole, right? It'd be very simple to color that in. Now, another type of removable discontinuity is that we do have a point, and let's say the function value exists up here. So f of A does exist. So either it's undefined and there's no point, or that point is just not the same as whatever the limit is. So the other reason that we could have a removable discontinuity is that the function value does not equal the limit value. Since the function value would be up here and the limit value would be here at this y value. And then an infinite discontinuity is just that. It's when we have a vertical asymptote and our function approaches either positive infinities, negative infinities on either side, or one of each, as we can see here. And in that case, we have a couple issues. We have f of A clearly is not defined because A is not in the domain, since it is a vertical asymptote, so A is a number that makes the denominator 0. So f of A is undefined, and also the limit as x goes to A does not exist here. The overall limit does not exist because we would not say an overall limit is infinity or negative infinity. So these are the three types of discontinuities, and we can see that the removable discontinuity is the easiest to fix because the limit exists, but our point just might not equal it, or our point might not be defined. So a removable discontinuity is the easiest to remove to make our function continuous. With jump and infinite, it's very hard to fix those to make those continuous. With a rational function like this here, in order to identify the point or points of discontinuity, we want to just see what makes the denominator 0. That's going to be the easiest way to identify them. And then we want to classify, right? We want to say, is it jump? Is it removable? Is it infinite? So let's take a look at the denominator. The denominator here is factorable. And so we can take this denominator and factor it. So we'll have x plus 1 in the numerator, and our denominator can be written as x minus 1, x minus 3. Nothing cancels top to bottom. X plus 1 and x minus 1 are close, but they cannot cancel. Therefore, the two values that make our denominator 0 are positive 1 and positive 3. So our discontinuities occur there. And x equals 3. Now, because there's no canceling and they just make the denominator 0 and nothing cancels out, both of these actually will be vertical asymptotes in our graph. And therefore, these are both infinite discontinuities. So this is an infinite discontinuity, and this one is as well. Let's take a look at the graph of this function just to confirm graphically. All right, I have this graphed on Desmos, and we can see that we do have vertical asymptotes here when x is 1 and when x is 3. X is 1 here, and so that's an infinite discontinuity, and then this would be the vertical line x equals 3. We can see that those are clearly the vertical asymptotes, and we can see if we zoom out even further that they're clearly the vertical asymptotes there. Our graph approaches positive and negative infinities on either side of them. And we can do a couple things. If we just take a look at the table, if we want to type in 1, well, we see down here already, if we type in 1, that's undefined, right? It makes our denominator 0. If we want to type 3, that would also make our function undefined. All right, in this next example, this looks almost the same, except here it's x minus 1, and I just called it g of x because we have a new function. But we're going to do the exact same thing with factoring because it's a rational function and it's factorable. So we'll have x minus 1. In the denominator, we'll have x minus 1 and x minus 3 again. And we can clearly see that 1 and 3 make our denominator 0. So once again, we have discontinuities at x equals 1 and at x equals 3. But now something special can happen. The x minus 1 factors cancel. We removed those factors. Therefore, x equals 1 is now considered a removable discontinuity. It is a removable discontinuity, no longer an infinite. Now, this factor does not get removed. It does not get canceled. Therefore, x equals 3 is still a vertical asymptote. It is still an infinite discontinuity. And if you didn't realize, D/C means discontinuity. Okay, here's the graph of this function. Note how different it looks just by changing the numerator to the x minus 1. Again, we can clearly see that there's a vertical asymptote at the line x equals 3 right here. So that is an infinite discontinuity. I'm not going to dash it in because every time I do that it gets all wonky on here, but just imagine the vertical asymptote drawn here, dashed. And then at x equals 1, we can't see this removable discontinuity. Recall from the start of this video that a removable discontinuity is an open hole, but I can show you how you can see this on Desmos. If you hit this little plus in the corner, it looks like if I move, look, 1 is here. So if I move along, I'm getting closer and closer to when x is 1, and when x hits 1, it's right there. There is an open hole there. It says 1, undefined. There really is an open hole. If you were to graph this by hand, there should be an open hole at the coordinate point 1 where it should be. And that is showing that that is the removable discontinuity there. Now, what coordinate point would that be? Let's figure that out. All right, let's see where that hole would be on our graph, and then we can look at the graph just to confirm. This new function that we have now created, we've canceled these x minus 1s. Let's see what remains. We are left with a 1 in the numerator and an x minus 3 down here. If we plugged in 1 into this function, we'd have 1 over 1 minus 3, or 1 over negative 2, negative 1/2. So the hole in this function would be at 1, negative 1/2. That's where our graph would be. Since we removed the issue, the removable discontinuity, we have this new function that's now graphed, and this is just where the hole is in that function. Let's check and see if that's where it would be. As we're scrolling here, the coordinate point 1, negative 1/2 would be here, but there is actually an open hole there because it is a removable discontinuity. For this piecewise function, we want to find and classify each point of discontinuity. The first thing that we should look at in a piecewise is all these functions here, these three functions, are there any where we would have discontinuity, meaning would we have an x in a denominator anywhere? Well, no. This is just a line. It's continuous everywhere. This is a horizontal line, y equals 2. it's continuous everywhere. And this is also a line, 1/2 x, continuous everywhere. There's no x in a denominator, so we don't need to worry about that. What we do need to worry about, though, is looking at the breaking or changing points. And it looks like when x is 2, that's when stuff changes. In fact, what's happening is different when x is less than 2, when x is actually 2, and when x is greater than 2. So what we need to do is figure out if we are continuous or discontinuous at 2. All right, so let's see if we're continuous at x equals 2. We're going to do our checklist. The first thing we want to do is find f of 2. And that's easy. When x is 2, our output is also 2. So f of 2 is 2. It's defined. The second thing is we want to look at the limit as x approaches 2 of our function. And in order to do that, we have to look at the left-sided limit and the right-sided limit, which I'm not doing super mathematically. I'm just writing L and R for left and right. As we look at the left-sided limit, it would be 3 minus 2. So our left limit would be 1. And our right limit, we'd look here, and we plug in 2 over 2, that's 1. Awesome, so our overall limit is 1, so our limit exists. Then the final checklist for continuity is, does f of 2 equal the limit as x approaches 2? No. 2 does not equal 1. So we do have a point of discontinuity when x is 2. Let's sketch the graph of this and see what it looks like. The first thing we'll sketch is 3 minus x. So I'll start up at 3. And we have a -1 slope. And I go right until we're at less than 2. So I have an open hole there. So it looks just like that. Then the next thing I'm going to sketch is this, which is basically the coordinate point 2, 2. So it's right there. Great. Then the last thing I will sketch will be the line 1/2 x, or x over 2. And it looks like we would start, I want only greater than 2, but if I were to start graphing, I'd start at the origin, go up 1 over 2. Okay, I can't go there, but then I go up 1 over 2, so I have it here. Up 1 over 2, and it just doesn't hit there. All right, so that's this kind of weird piecewise function. You could also do this on Desmos as well. But if we take a look, we can clearly see that the limit exists, right? We said that the limit's 1. Yes, as we approach from the left and the right of 2, our limit is 1, but our function value is 2. This type of discontinuity where the limit exists, but the function either is undefined or is elsewhere, like in this case, that's a removable discontinuity. So we would say x equals 2 is a removable discontinuity. In fact, how would we change this in order to make it continuous at 2? Well, all I'd need is we'd need to fill this hole in here instead of having it up here. So instead of having this be 2 when x is 2, we'd want it to equal 1. So in order to fix this, we can make it 1 instead, and then we'd have the coordinate point 2, 1, and we would be continuous all the way through. We would no longer have that point up there. So we could make it continuous. That's why a removable discontinuity is so easy to remove to make the graph continuous. For this next piecewise function, we want to see if either of the functions have potential x in the denominator. They don't. This would be continuous, it's a parabola. This would be continuous, it's a line, a linear function. And we can see that our breaking point or our changing point is when x is 0. So that's where we really need to care about seeing if it is a point of discontinuity or not. So let's do our checklist for continuity for x equals 0. So at x equals 0, are we continuous? All right, let's see. First, So I'll put continuous. Oops. All right, so we want to see what is f of 0. Function value at 0 would be 0 squared plus 1, so it's 1. The second thing we want to look at is what is the limit as x approaches 0 of our function. And because 0 is a breaking point, we have to check both the left-sided limit and the right-sided limit. Again, I'm being lazy and not writing out the exact notation. I'm just putting L and R for left and right. If in your work you want to just do that, that is totally fine as well. But the left-sided limit, we'll check here. Plugging in 0 is something we already did. And then the right-sided limit, we'll check here. So 0 minus 3, that's negative 3. So our overall limit does not exist. So clearly we're not continuous at x equals 0. We don't even have to go to check part number 3. So we are discontinuous at x equals 0. Now what type of discontinuity is it? Instead of graphing by hand, I'm going to go to Desmos to just take a look at it. But if we sort of think about what's happening, our left and right-sided limits are not matching up. So it seems to me like there might be a jump. Let's take a look. All right, I have our piecewise function graphed. And those of you that struggle with graphing the piecewise, here's how you do it, right? We have to put not only our function in, but then the special brackets about where this function exists. So here's our parabola, and then here's our linear function, our line. And I put this kind of janky looking open circle there because we can't really see that well on Desmos. But we can clearly see that the limit as we approach 0 from the left is 1, and the limit as we approach 0 from the right is negative 3. Therefore, the overall limit as we approach 0 does not exist. And this is a jump discontinuity. We are jumping from one height to another height. It's not infinite, there's no vertical asymptotes here, and it's not removable. We can't just fill in the hole and make it work. There is clearly a jump here. So when we have a piecewise and the limits from the left and the right are not equal, but they both exist, they're ending at different spots. There is a big jump there. So that is why the discontinuity at x equals 0 is a jump discontinuity. So we would say we have a jump discontinuity at x equals 0. Now we've talked about a lot of discontinuities. We've looked at a few different functions, 2 of them being piecewise. And really, if you're struggling with what type of discontinuity something is, I really recommend graphing it either by hand or on Desmos just to see. Let's end with an analysis of the graph here. We can see that this is definitely a piecewise function, and there's a vertical asymptote going on, some open circles, some closed circles. So let's take a look and look from left to right and identify our first point of discontinuity. It looks like our first point of discontinuity is going to be when x is negative 2. So our discontinuities are going to exist at x equals negative 2. Our second discontinuity will exist here at x is 1. And our next discontinuity exists when x is 4. Those are the 3 on here. Let's classify them. So at x equals negative 2, the limit exists. The limit as x approaches negative 2 from both sides is 3, so the overall limit definitely exists. We just have an open circle here. The function's also defined. This is called a removable discontinuity because it's so easy to remove. We could so easily make this point just go here instead on our piecewise. We could cross off a number. Instead of saying it's up at 5, we could say just put it at 3. Problem solved. So here, this is a removable discontinuity at x equals negative 2. Let's take a look at when x equals 1, right here. The limit as we approach 1 from the left is negative 3, and the limit as we approach 1 from the right is 4. Therefore, the limit does not exist as x approaches 1. This is not an easy fix. This is a jump discontinuity. our left and right-sided limits both exist, but they're different numbers, and it's just a mess. So because there is a literal jump there, this is a jump discontinuity. And the last one is at x equals 4, here. The limit as we approach 4 from the left would be negative infinity, and the limit as we approach 4 from the right is positive infinity. Therefore, the overall limit as x goes to 4 does not exist. We have a vertical asymptote at x equals 4. A vertical asymptote means that that is an infinite discontinuity. Our one-sided limits are approaching the infinities on either side. So a vertical asymptote means that that is an infinite discontinuity. Those are the three types of discontinuities that we will be studying this year in calculus: removable, jump, and infinite. After today's lesson, you should be able to look at a graph visually and decide where there are points of discontinuities and which of the three they are. We can also look at a couple different functions, and by using our checklist for continuity and then perhaps graphing the function just to get a visual, we can also decide where and what type of discontinuities we have.